In this video, we're going to go through and find Taylor series and Taylor polynomials for some functions that may be a little more complicated, but are sort of based on some of our building block Taylor series. So first one here, these are all going to be centered at x equals 0. First one, we are going to have sine of x squared. So when I see sine of x squared, the building block here is going to be sine of x. So the Taylor series for sine of x, this is something you can memorize or look up as you need this. This is n equals 0 to infinity. It's negative 1 to the n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. So that's our sine of x series. And essentially the way sine of x squared differs is I'm just putting x squared in where I see x. So what I'm going to do is I'm going to do sine of, I'm going to write this, how about in red here, my x squared equals then sum n equals 0 to infinity, negative 1 to the n plus 1, and then I'm going to put an x squared where the x was originally. So x squared to the 2n plus 1 over 2n plus 1 factorial. Here, so essentially all I did was put an x squared where the x was, and then I'm going to go and sort of simplify that x squared to the 2n plus 1. This is a, oh, sorry, no, I have the wrong series here. Sorry, I messed up. The sine x should be just a negative 1 to the n here. Whoops, sort of not really thinking this through, right? Sorry, it should start positive. So sine x should be negative 1 to the n here. And then I'm going to get, let's see, x squared to the 2n plus 1. That's going to be x to the 4n plus 2, 2 times 2n plus 1, over 2n plus 1 factorial. And there's our Taylor series centered at 0 for sine of x squared. So pretty easy to do. Much simpler, probably, than just taking derivatives of sine of x squared, evaluating those at 0 here. Next one. We have x squared times natural log of 1 plus x cubed. So let's look at this here. So we've got x squared times natural log 1 plus x cubed. Well, here, I'm going to look at this. This is a product. The x squared, that's just going to sort of multiply or increase the exponent on the x's inside of the series. So the x squared we can deal with later. Natural log 1 plus x cubed, that looks a lot like natural log 1 plus x, but I'm plugging in x cubed instead of x. So what I'm going to do is I'm going to use a series for natural log 1 plus x. And this is one that we sort of need to go look up, I guess. And this is going to be n equals 1 to infinity, negative 1 to the n plus 1, and then we get an x to the n over n here. So this should be our series for natural log 1 plus x. And what that means here is that if I do x squared times natural log 1 plus, let's write the x in red again, or the x cubed, I'm going to get, okay, now I have an x squared on the outside, but then times my series, n equals 1 to infinity, negative 1 to the n plus 1, and then I have my x cubed goes in place of the x in the original series, x cubed to the n over n. Let's just go down here. So that's x squared times the series, n equals 1 to infinity, negative 1 to the n plus 1, over x cubed to the n is x to the 3n over n. Now, I want to bring this x squared inside my series. So that's sum n equals 1 to infinity, negative 1 to the n plus 1. I'm going to write this as x squared, whoops, times x to the 3n over n. So I can bring the x squared in as a factor of the inside, and then x squared times x to the 3n is x to the 2 plus 3n, or x to the 3n plus 2. So my answer here is n equals 1 to infinity, negative 1 to the n plus 1, x to the 3n plus 2 over n. There. Again, we're able to use a known series to basically calculate this relatively easily. We didn't have to take derivatives, which would get annoying with product rules and things like that here. Next one. we've got x cubed over 4 minus x. Okay, this one, I've got the x cubed. I can kind of just bring that inside of a series. So I'm going to view this as x cubed multiplied by 1 over 4 minus x here. Now, what I know here is the series I'm going to use as sort of a building block is 1 over 1 minus x is a sum n equals 0 to infinity x to the n. So I've almost got that, but I have this 4 here, the 1 over 4 minus x. It's like 1 over 1 minus x, but there's a 4, so I need to change that 4 to a 1. So what I'm going to do, I'm going to do x cubed times 1 over, I can factor 4 out of my denominator. That'd be 4 times 1 minus x over 4. And then what I get is really x cubed over 4 times 1 over 1 minus x to the 4th. So I took x cubed over 4 minus x, rewrote that to be some small, I guess really monomial, I was going to say small number of termed polynomial, it's really a monomial, times something where we can find the actual series for. So what we're going to get then, coming down here, this is going to be x cubed over 4 times, and then we're going to do a sum n equals 0 to infinity. Instead of x to the n, we're really going to get x to the 4th to the n. So I'm plugging in x over 4 for x in 1 over 1 minus x. And what that's going to give us is x cubed over 4 times the series n equals 0 to infinity, x to the n over 4 to the n. And then I can bring the x cubed over 4 inside of that series. So that's a sum n equals 0 to infinity, x cubed times x to the n over 4 times 4 to the n. And then what I get is a sum n equals 0 to infinity of x to the n plus 3 over 4 to the n plus 1. Here. Now you could leave that there. Some people would like to rewrite x to the n plus 3 as x to the n. If you wanted to do that, I get n equals 0 to infinity. I want to get x to the n. I have to sort of replace n. Oh, sorry, it's not going to actually go 0 to infinity down here. I have to replace n with n minus 3. So I'll get 4 to the n minus 2. No, n minus 2 is 2 less than n plus 1, 2 less than n plus 3 there. And I went sort of down 3 in my exponent on x, or sort of on the inside, means I'm going to go up 3 on the outside. So it'll be n equals 3. So you can either give this answer more sort of a traditional power series. I'd be okay if you left it x to the n plus 3 here. Either one will really work for most of our purposes here. Next one. We have 3 over 1 minus x quantity squared. So this one's going to take a little more work here. And the problem is I don't have a known series in my head for 1 over 1 minus x quantity squared. So the 3 doesn't bother me. So I'd like to think of 1 over 1 minus x squared. I'd like a series for this. I don't have that. What I do have is 1 over 1 minus x here. So what I'm going to do here is I'm going to differentiate 1 over 1 minus x. That's a derivative of 1 minus x to the negative 1. So I bring my exponent down, I get a negative 1 times 1 minus x, decrease the exponent, do negative 1 minus 1 is negative 2. And then by chain rule, I have to multiply by the inside, the derivative of the inside. That's derivative of 1 minus x. That's another negative 1. So the negative ones will cancel out. And this actually gives me my 1 over 1 minus x squared. So that tells me 1 over 1 minus x squared, it's the derivative of 1 over 1 minus x. Here, which is the derivative then of the sum n equals 0 to infinity, x to the n. Here's our power series for 1 over 1 minus x. And given certain convergence results, I can move that derivative inside the series. And that just gives me a sum n equals 0 to infinity n times x to the n minus 1. Now, it'd be customary here, I can drop the n equals 0 term, because when n is 0, this sort of term inside 0 times x to the 0 minus 1, that's just 0 because n is 0. So what we get here is, let's see, sum n equals 1 to infinity, n times x to the n minus 1. And then I'd like to write this x to the n minus 1 sort of just as an x to the n. So to do that, I'm going to have to replace n with n plus 1. So I'll get n plus 1 x to the n. And when I go up 1 inside in my summand, I have to go down 1 in my index. So that n equals 0 to infinity. So this is my series for 1 over 1 minus x squared. So I had to do some work there. I had to differentiate a known series. But once I get that, that tells me 3 over 1 minus x, quantity squared, is 3 times 1 over 1 minus x, quantity squared. That's 3 times the series n equals 0 to infinity, n plus 1 x to the n. And, I mean, I could rewrite this by bringing the 3 inside. It's just 3n plus 3, maybe, or 3 times n plus 1, x to the n. So there's a power series for 3 over 1 minus x, quantity squared. They are Taylor series. All right, next one, we have 5 over 2 minus x cubed. So 5 over 2 minus x cubed. This looks very similar to the last question, except I have a degree 3 on the bottom. So what I'm going to do is I'm going to do 1 over 1 minus x, quantity squared, and I'm going to differentiate that. Here. So what I'm going to get is I'm going to get a derivative with respect to x, sum, and then I have to use this sort of series that we got from the last question. That was n equals 0 to infinity, n plus 1 times x to the n. And again, I can bring my derivative inside of this series. That's n plus 1 times derivative with respect to x, x to the n. Note, I can sort of, the n plus 1 is a constant as far as the derivative with respect to x is concerned. There's an n there, but there's no x here. And so what I get is sum n equals 0 to infinity, n plus 1 times n x to the n minus 1. And I can do the same thing I did before. If n is 0, I have a factor of n that makes the term on the inside 0. And so what I get is a sum n equals 1 to infinity, n plus 1 times n x to the n minus 1. So I can just drop the n equals 0 term. And then I'm going to shift my indexes. I want to replace n minus 1 with n. That means I'm going to replace really n with n plus 1. So I'm going to get an n plus 2 times n plus 1 times x to the n. And then if n was n plus 1, when n was 1 before, n's got to be 0 now. So you can check if you did this shifting right. On the new one, if you plug in n equals 0, you get 2 times 1. Old one, if you plug in n equals 1, you get 1 plus 1 is 2 times 1. So they should sort of match here. Okay, and that's a series for the derivative of 1 over 1 minus x squared. I actually should take that derivative just as a function, forget the power series here. So I do a derivative, 1 over 1 minus x squared. I probably should have done this first here because I just sort of assumed I'm going to get something with a 1 minus x cubed in my denominator. Probably should have checked that because if I don't, this original series was sort of wasted effort. So this is 1 minus x to the negative 2. It's going to give me a negative 2 times 1 minus x. Negative 2 minus 1 is negative 3. Derivative of the inside is negative 1. So that's 2 over 1 minus x cubed. So we know that that 2 over 1 minus x cubed equals, literally as a Taylor series of n equals 0 to infinity, n plus 2 times n plus 1 times x to the n. Because both of them are derivative with respect to x of 1 over 1 minus x squared. All right, so we got a series for that. Now, what we wanted, though, was 5 over 2 minus x cubed. All right, so this 2 we want to be a 1. This 5 we'd like to be a 2. So let's worry about the 2 being a 1 first. So what I'm going to do is I'm going to have 5 over, I can write this as 2 times 1 minus x over 2, and that whole thing cubed. Here, so I can factor a 2 out of the inside, or 2 out of 2 minus x here. And then what I get is 2 to the third is 8. So I'm going to pull out the 5 over 8, and that's times 1 over 1 minus x over 2 cubed. But actually in my my series formula, I want a 2 on top. So then I'm going to multiply top and bottom by 2, and that will give me a 5/16 times 2 over 1 minus x over 2 cubed. So I just rewrote 5 over 2 minus x cubed as 5/16 times 2 over 1 minus x over 2 cubed. Purpose of that, again, was I could use my series formula that I sort of derived just before this, and I can replace the 2 over 1 minus x over 2 cubed with the sum n equals 0 to infinity. It's n plus 2 times n plus 1 times the thing that 1 minus, okay, that's an x over 2. So in place of our x to the n, we're going to get x over 2 to the n. And so what you'll get then is a sum n equals 0 to infinity. You'll get a 5/16. Let's just write it this way. You get a 5 on top, 16 on the bottom. The n plus 2 and n plus 1 are on top. Let's see, we'll get an x to the n on top, and you'll get a 2 to the n on the bottom. So this, I could leave this here. Something I would see that I might contemplate doing is I'll notice 16 is 2 to the 4th. And so you could rewrite this as n equals 0 to infinity 5 times n plus 2 times n plus 1 times x to the n of over 2 to the n plus 4. I guess you could do that. It's not really necessary. Sometimes I would actually just leave the 5/16 out in front as well here, because it's not really that big a deal. I have to leave the 2 to the n inside because it has an n in it. Next one. Way back up to the top here. Okay. So this one we've got 3x over 1 minus x squared. Note it's not quantity 1 minus x squared, it's 1 minus the quantity x squared. So we have 3x over 1 minus x squared. This one I'm going to rewrite as 3x times 1 over 1 minus x squared. And then I'm going to use the series formula. 1 over 1 minus x is the sum n equals 0 to infinity, x to the n. So then what I can do, this is 3x times, now this is 1 over 1 minus x squared. So I put an x squared where an x is. 1 over 1 minus x, replace the x with an x squared. So I get sum n equals 0 to infinity. And then that x to the n becomes x squared to the n. And so that gives me 3x times sum n equals 0 to infinity, x to the 2n. Pretty ugly infinity there. And then I can bring the 3x inside. So n equals 0 to infinity, 3x times x to the 2n. This is x to the 1 times x to the 2n. I'm going to put an answer down of n equals 0 to infinity, 3 times x to the 2n plus 1. Now, sometimes I'd want to write that as x to the n, but here's odd powers, so I'm not really even going to bother with that. It's sort of probably ways to do that, but they're going to look uglier than the way we've got this. Next. Okay, we did sine of x squared, but now this is sine squared of x. So this is sine squared of x here. And there's multiple ways to attack this one. You could take this series for sine of x and try and square that. Generally, multiplying power series or Taylor series is going to get a little bit ugly, so I'd prefer to avoid that. So what I'm going to do is use a trig identity instead. And I know one of my trig identities says sine squared x is 1 minus cosine 2x over 2. And I look at this and I say, okay, 1, I don't need a Taylor series at all, it's just 1. Cosine 2x, I can actually find a Taylor series for that, and I don't have to multiply that by another series. So this looks promising. So what I need is a series for cosine x, and you can look this up or hopefully have it memorized eventually. This is like the series for sine x, but it's even terms. So it's negative 1 to the n, x to the 2n over 2n factorial. So then my 1 minus cosine 2x, I'm going to write this as 1/2. Well, no, let's do it this way. Let's do it as 1 minus over 2. Let's just put the series in for cosine 2x here. So I get sum n equals 0 to infinity. I get a negative 1 to the n. Now instead of x to the 2n, I get a 2x to the 2n over 2n factorial. That's all over this 2 here. So I get 1 minus sum n equals 0 to infinity, negative 1 to the n. See, 2 to the 2n times x to the 2n over 2n factorial, whole thing over 2. Okay, now what I'm going to do, well, let's do 2 to the 2n here before we start getting overly complicated here. I'm going to write this as 1 minus 2 to the 2n. Let's just go off to the side maybe here. 2 to the 2n is 2 squared to the n. That's 4 to the n, which is just sort of generally a nicer way to write that. So I'm going to do sum n equals 0 to infinity, 4 to the n, x to the 2n over 2n factorial, all over 2. Now, what's going to happen? When n is 0 in my series, I'm just going to pull that term off here because I want to combine it with the 1 here. So the 1 is sort of a degree 0 term, so I'm going to pull off the degree 0 term. Well, when n is 0, you get 4 to the 0 is 1, x to the 0 is 1, 0 factorial is 1. So you get 1 minus 1 plus sum, and then my sum goes n equals 1 to infinity. 4 to the n, whoops, made a mistake in the previous one. I lost my negative 1 to the n. So I should have had a negative 1 to the n in my series for the cosine. So n equals 1 to infinity. Negative 1 to the n, 4 to the n, x to the 2n over 2n factorial, all over 2. Now, 1 minus 1, that's 0. So I get a negative, and then I can bring the 2 up from the bottom. I get a negative 1/2. Sum n equals 1 to infinity. Negative 1 to the n, 4 to the n, x to the 2n over 2n factorial here. And then I'm going to bring the negative 1/2 inside my series. So I get n equals 1 to infinity. So the negative 1/2 is negative 1 over 2 times negative 1 to the n. I'm going to do a 2n factorial, and I'm noticing something here where I did some work, and I switched 2 to the 2n to 4 to the n here, but now I'm realizing I have a 2 in the denominator. So I probably didn't really want to switch that 2 to the 2n to 4 to the n because I want to cancel a 2 here. So I'm going to go back and go that 4 to the n is 2 to the 2n. And I have an x to the 2n. And then when all is said and done here, n equals 1 to infinity. I have a negative 1 times negative 1 to the n. That's negative 1 to the n plus 1. 2 to the 2n, and I divide by 2. It's going to decrease that exponent by 1. It's 2 to the 2n minus 1. I have an x to the 2n. And then I have a 2n factorial on the bottom. So this was a Taylor series, again, for sine of x squared. I'm sorry. Did I say that wrong? I wrote it wrong. Not sine of x squared we did before. This is sine squared of x. There we go. And again, the strategy was to use a trig identity 1 minus cosine 2x here and just get a series for cosine 2x and sort of calculate away. All right, next one. We have sine x minus x. So we're looking at sine x minus x. This one's going to work out pretty well here. What I'm going to do is use a series for sine x. I'm just going to replace sine x with the series. It's n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So this is really my sine x, and then I'm subtracting x. Now, to subtract x, what I'm going to do is expand out this sine x series, pull off the sort of degree 1 term. That's when I get an x. I'll note that's when n equals 0. So I'm going to do the n equals 0 term. When you do n equals 0, you get negative 1 to the n. Well, it's 1. X to the 2n plus 1. That's 0 plus 1. That's x. And then I'll get a 1 factorial on the bottom. That's just 1. So the n equals 0 term is x. And I'm going to say it's x plus n equals, then I do the terms 1 to, with n is 1 to infinity. Negative 1 to the n. X to the 2n plus 1 over 2n plus 1 factorial. So that's what's really in the parentheses. I just rewrote that series by pulling off the first term, minus x, and you'll notice the x and the minus x cancel. And so what I get is just n equals 1 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So this is really our original just sine x series here, but the only thing that changes is that n equals 0, that normally we have for sine x, changes to a 1 because we subtracted off the first term. It's really all the minus x is doing. Next one. Cosine x minus 1. This is going to be very similar here. So if I do cosine x minus 1, cosine x is sum n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. So that's my just series for cosine x, minus 1. And this minus 1, it's a degree 0 term. Note that's going to be n equals 0 for the cosine x. Or notice x to the 2n with sine, it was x to the 2n plus 1 here, so it's a little bit different. Very similar, though. And so what I'm going to get here is, so I'm going to pull off the n equals 0 term. I get negative 1 to the 0 is 1. 0 factorial is 1. X to the 0, that's 1. So I'm going to get 1 plus the sum n equals now 1 to infinity. And I get the same thing inside. Negative 1 to the n, x to the 2n over 2n factorial. Minus 1. Well, then the 1 and the minus 1 cancel. And what I get is an n equals 1 to infinity, negative 1 to the n, x to the 2n over 2n factorial. So that's cosine x minus 1. All right, next one, natural log 5 plus x. So let's look at this, natural log 5 plus x. Now, the series we have is natural log 1 plus x. This should be a sum, n equals 1 to infinity, negative 1 to the n plus 1, x to the n over n. So this looks like about the right thing here, but what I'm going to have to do is really change that 5 somehow to a 1 here. So let's work on natural log 5 plus x. I can try the same game I've had before, so I could write this as natural log 5 times 1 plus x over 5. So this is what we did with like 1 over 4 minus x or something like that. You factor out the 5, and then I have a 1 plus. Now here, at this point, I could use a rule of logs here. So rule of logs says I have a product on the inside, 5 times 1 plus x over 5. That's going to work out to be natural log 5 plus natural log 1 plus x over 5. What's handy about that is natural log 5 is just a constant here. So I can then use my series for natural log 1 plus x. So I get natural log 5. So I'm going to here down there. Plus, and then this natural log 1 plus x over 5 becomes sum n equals 1 to infinity, negative 1 to the n plus 1 times not x to the n, but x over 5 to the n, all over n. And from here, what we're going to get is, let's see, we have a natural log 5 plus, and I'm just going to write this as sum n equals 1 to infinity. I have my negative 1 to the n plus 1. I have an x to the n from x over 5 to the n. I'm going to get an n times 5 to the n. 5 to the n I can put on the bottom. So there's my series. I don't want to combine this natural log 5 into the series because it's not going to have the same formula. I mean, I could make a sequence where I say, an equals -1 to the n plus 1 over n times 5 to the n for n greater than or equal to 1, and a0 is natural log 5, but that just seems sort of awkward here. I guess technically maybe that's what I should be doing, but this is really your series for natural log 5 plus x. All right, next group of problems. Here. Now this one, so find these groups here, this whole sheet. Find the first 4 non-zero terms of the Maclaurin series for each function. So Maclaurin series, that means it's really a Taylor series centered at 0. That's what we've been doing, just with a different name here. And now we only want the first 4 non-zero terms. So in some sense, we're finding Taylor polynomials. Now, not of order 4, because there might be like a missing term that's not 0 here. So let's start with the first one. We have e to the x times cosine x squared. Here. So what I'm going to do is convert both e to the x and cosine x squared into series here. So what I'm going to get here is okay, the series for e to the x. That's n equals 0 to infinity, x to the n over n factorial. So that's just e to the x times cosine x squared is a sum n equals 0 to infinity, -1 to the n. Now, if it was x, it would just be x to the n, but we have an x squared, so this is x squared to the n over 2n factorial. Whoops, except not x squared to the n, sorry. It's x squared to the 2n. So that's my other series here. And then I can rewrite these n equals 0 to infinity, x to the n over n factorial, leaving the e to the x alone. The cosine is n equals 0 to infinity, -1 to the n. X squared to the 2n is x to the 2 times 2n. That's x to the 4n over 2n factorial. Okay, so I can write this out. And now it's essentially I'm multiplying two infinite degree polynomials here. Well, that would be infinitely long. I can't do that. But I only needed the first 4 non-zero terms. So what I'm going to do is I'm going to write out the first few terms of each of these and then kind of sort of think about how the multiplication would go as polynomials. So this first term, or first series, the e to the x, when n is 0, I get 1. When n is 1, I get x over 1 factorial, that's x. When n is 2, I get x squared over 2 factorial. 2 factorial is 2. When n is 3, I get x cubed over 3 factorial, which is 6. When n is 4, I get x to the 4th over 4 factorial is 24. And I'm going to just do a plus ... I might have to fill that in later. I've got 1, 2, 3, 4, 5 terms. So if all of the sort of terms are there, if I don't have any 0 coefficients, I'm going to expect to go up to x cubed. X to the 4th is already too far. But if some of these terms are 0, I'm going to have to need extra. So I'm just going to sort of do a little bit extra here. It won't hurt anything, really. Now, with the cosine part, I'm going to do n equals 0. It's going to give me a 1. -1 to the 0 is 1. 2 times 0 is 0. 0 factorial is 1. X to the 0 is 1. Next term, it's going to alternate. I'm going to get an x to the 4th over 2 factorial, which is 2. So already I'm up to degree 4. I'm going to do one more term here, but probably degree 4 is all I really need here. The next term, when n is 2, I'm going to get a plus 1. X to the 8th over 2 times 2 is 4 factorial. That turns out to be 24. And then plus some stuff. First one's actually a minus there. All right. So I wrote out part of this product. And now what I'm going to do is think about how do I get some of my leading terms. So I'm going to think about how do I get a constant term. Well, to get a constant term, I'm going to take a term from the left, sort of polynomial, times a term from the right polynomial. And all the ways when I multiply term from the left times term to the right, and I get a constant. Well, there's only one way to do that. It's 1 times 1 here. So I'm going to take really my 1 times my 1. That's going to give me a 1. Now I'm going to worry about how do I get an x. Well, the only way I'm going to do that really is 1 times x. So that's 1 plus x. How do you get an x squared? I've got to take a 1 on the right, because if I do x to the 4th, that's degree higher than 2. So it's going to be 1 times x squared over 2. which is just x squared over 2. X cubed over 6, same thing. So this actually worked out pretty fortunately. I've got 4 non-zero terms. This is plus some other stuff here. So my answer is really these are the first 4 non-zero terms. That's really a Taylor polynomial of order 3. Here. Okay. Next one. We get e to the x times natural log of x cubed plus 1. We get e to the x times natural log. I'm going to write that as 1 plus x cubed instead of x cubed plus 1. Doesn't really matter. I'm going to play the same game as before. This is sum n equals 0 to infinity, x to the n over n factorial. That's my series for e to the x. And then natural log is a sum n equals 1 to infinity. It's a negative 1 to the n plus 1. It's a x to the n, but I don't have natural log 1 plus x. I have natural log 1 plus x cubed. So that 1 plus is part of sort of the natural log power series. So x cubed to the n over n. Here, and then x cubed to the n is x to the 3n. So I get n equals 0 to infinity. Whoops. You get x to the n over n factorial times sum n equals 1 to infinity, negative 1 to the n plus 1, x to the 3n over n. All right, and now I'm going to do the same thing as before. Write out the first few terms here. I need to get up to probably at least x cubed. I might go a little bit farther than that just to be safe in case I get some 0 terms here. So I'm going to get is the e to the x again is 1 when n is 0. When n is 1, 1 factorial is 1, so that's just x. N is 2, I get x squared over 2 factorial is 2. N is 3, I get x cubed over 3 factorial is 6. N is 4, I get x to the 4th over 4 factorial is 24. The natural log 1 plus x cubed series, when you plug in a 1, you get a, sorry, n is 1, you get 1 plus 1 is 2. You get a positive, it's going to give me x cubed over 1. Do n equals 2, I'll get a negative, and that'll be x to the 6th over 2. Next term when n is 3 is x to the 9th over 3, plus blah, blah, blah. Actually, next one's a minus here. And I'm already well above the degree I have in the e to the x. So really, for this x to 9th come into play, I need to go at least up to x to the 6th on the left as well. Which I might have to do if things cancel out. It's probably unlikely. All right, so here, I'm going to look at this, and I'm going to say, well, how do I get a constant term? Well, I get a 1 times, well, I don't have a constant. So on the right, I have to take something that's at least x cubed. So that means if I multiply a term from the left times a term from the right, I'm going to get something at least degree 3. So I'm going to start at x to the 3rd. I'm going to get x to the 3rd. Then I'm going to get x cubed times x. That's to get x to the 4th. There's no other way to get x to the 4th. X to the 5th. X cubed times x squared over 2. That'll give me an x to the 5th over 2. I already have 3 terms. But now when I do x to the 6th, something kind of different happens. I get x cubed times x cubed over 6. That's x to the 6th over 6. But I could also do negative x squared over 2 times 1. Sorry, negative x to the 6th over 2 times 1. So I get a negative x to the 6th, sorry, x to the 6th over 6 minus x to the 6th over 2 as my x to the 6th term. So that's going to be my 4th non-zero term. And then I could, do sevenths and so on here, but I don't need those. And so what I'm going to get here is x cubed plus x to the 4th plus a half x to the 5th. And now I have 1/6, really minus a half. That's 1/6 minus 3/6. That's negative 2/6. That's actually negative 1/3. So I get minus 1/3 x to the 6th. Here. And so that's your sort of first 4 non-zero terms of the Taylor series for e to the x times natural log 1 plus x cubed. Next question. What do we got here? We've got 1 over 1 minus e to the x. We've got 1 over 1 minus e to the x. Now, this one's a little different. It's a composition here. So essentially what I've got here is this is a 1 over 1 minus x. So let's just remind ourselves here. 1 over 1 minus x. That's a series n equals 0 to infinity, x to the n. And inside of that, we're going to put an e to the x. So you could put an e to the x in here, but we want this to be a polynomial here. And so what we're going to do is put in a series for e to the x inside of the other series. That feels a bit weird. We're going to get n equals 0 to infinity. This is x to the n over n factorial. So what we're going to get here is 1 over 1 minus e to the x. I'm just going to write this out here as, so 1 over 1 minus x. That's 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th, and so on. And then e to the x, that's 1 plus x squared over 2 plus x cubed over 3 factorial is 6 plus x to the 4th over 4 factorial is 24, and so on. And so what I'm going to get is I need to put this whole thing for e to the x inside of each of these x's here. So what I'm going to get here is, actually I'm going to get trouble here. So what's going to happen here, this normally could work out. Did I actually write the right things down? Yep, that's what I've got. So what would happen is this is 1 plus, and then where this x is, I put sort of this series. So 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus blah, 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 plus, and then I do the same thing, 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus blah, 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 squared. And then plus 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus blah, 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 cubed plus 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus blah, blah, blah to the 4th, and then there's more and more of those terms. Now, the problem here, really sort of what I would do is sort of square this out here and just sort of look for the first so many terms. So what we're going to get here is 1 plus, this first one is just 1 plus x squared plus x cubed plus x to the 4th. Now I'm looking for the first 4 non-zero terms, so I'm only really going to go up to x cubed here. So I'm going to get 1 plus x, whoops, missed my x, 1 plus x squared over 2 plus x cubed over 6 plus some stuff here. But then when I do the square, I have to take one of these terms here times another one of the terms. So I could do 1 times 1, that'll give me 1. 1 times x, that'll give me an x. 1 times x squared over 2 is x squared over 2. 1 times x cubed over 6 is x cubed over 6. But then I could do the same thing with x. X times 1 is x. X times x is x squared. X times x squared over 2 is x cubed over 2. And then if I go any further, I'll get x to the 4th and higher. And then I'll keep going here. Now, x squared over 2 times 1 is x squared over 2. Let's see. X squared over 2 times 1 is x squared over 2. X squared over 2 times x is x cubed over 2. And then the x cubed over 6, I'll get a plus x cubed over 6 plus some stuff. So inside this left parenthesis and this right parenthesis, I wrapped the screen there. That's like my 1 plus x squared over 2 plus x cubed over 6 plus x over 24 squared. Here it's all the terms up to x cubed. And you could combine these together and add them up. I could do the same thing with a cube here. I could really go up to 1 plus x squared over 2 plus x cubed over 6. Take that cubed, write these up here. And this process would work out, and then you just sort of find sort of group-like terms, add those up, and it would work out just fine. Problem is, let's look at the constant term. What do I have? I have a 1. When I do the 1 plus x squared over 2, so forth, just the e to the x, I pick up a 1. When I do the 1 plus x, really my e to the x series squared, I can choose a 1 and then a 1. That gives me a 1 here. When I do the cubed, I could choose, I'm going to do 3 of these. So I could do 1 times x squared over 2 times x cubed over 6, or x times x to the 4th over 24 times x squared over 2. If I choose 1 and 1 and 1, I get another 1. X to the 4th, I could choose 1 4 times in a row. That gives me a 1. What's going to happen here is that I'm going to get a 1 for every single term here. That means my constant term is going to go to infinity, which means my series just does not work here. So here what we get is 1 over 1 minus e to the x really does not have a Maclaurin series. Here. Why? Well, what happens when you plug in x equals 0? If you do 1 over 1 minus e to the 0, you get 1 over 1 minus e to the 0 is 1. That's 1 over 0, and that's undefined. So you sort of pick up the infinity there. So this one, there's a process that would have worked out. It would have been kind of a mess here. Turns out, just does not work. All right, so next one, see if we get something nicer. Oh, no, that was actually, well, no, sorry. Next row, we got more coming here. So next one, we have sine x over 1 minus x. So we have sine x over 1 minus x. Now, what we're going to get here is I'm going to rewrite this as sine x times 1 over 1 minus x when I'm sort of recognizing that I have a power series for both sine x and 1 over 1 minus x. So this is going to be our series for sine x is n equals 0 to infinity. This is negative 1 to the n, x to the 2n plus 1. Sine is odd, so I get odd things inside here. 2n plus 1 factorial. And then the series for 1 over 1 minus x is just x to the n. And so what I get here, let's write out our series for sine x. That's x minus, when n is 1, 2n plus 1 is 3. So it's x cubed over 3 factorial is 6. Let's see, when n is 2, I get x to the 5th over 5 factorial. 5 factorial is 120. And then there's some more stuff, which again, I might need, but I'm going to hope I don't, essentially. X to the n is 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th, and so on. And then I just try and find the lowest degree terms first. So the smallest degree term is I take the leading term from sine x to the x. Leading term from 1 over 1 minus x, that's the 1. X times 1 is x. So I can get x that way. And then I'm going to think, how can I get x squared? Well, I'm going to have to choose an x from the left because x cubed is too big. So x times what gives me x squared? X times x gives me x squared. Okay, now how do I get an x cubed? Well, I could take x from the left times an x squared on the right. It's an x cubed. Or I could take x cubed over 6 on the left times 1 on the right. So I'll get a minus, essentially 1/6 x cubed. 2 3 terms. How do I get x to the 4th? I could choose x on the left times x cubed on the right. That's x to the 4th. Or I could do minus x cubed over 6 times x on the left. So it's a minus 1/6 x to the 4th here. And then there's some higher degree terms, but we already have 4 exponents here. And then I should do my subtractions. I have x plus x squared. 1 minus 1/6 is plus 5/6 x cubed. 1 minus 1/6 is plus 5/6 x to the 4th. And then it's really plus some more stuff here, but that's the first 4 non-zero terms. Next one. So we've got cosine of e to the x. So that's like that one we did before that didn't work out. This one is going to work out, or should. At least right away, I'm thinking, oh, the problem was that 1 over 1 minus e to the x. If you plug in 0, you get infinity here. But if I do cosine of e to the 0, what's that? That's cosine of 1. Now, I don't know what that is here, but it's some number. So this should work out. So what we're going to get here, cosine, let's write it out a little differently. This is n equals 0 to infinity, negative 1 to the n. Well, sorry, it's x to the 2n, typically for cosine, but we have an e to the x to the 2n over 2n factorial. Now, what we're going to do here is we're going to write this as a sum n equals 0 to infinity. Now when n is 0, I'm going to get e to the x to the 0. So that's actually just going to be, sorry, it's not right, n equals 0 to infinity. Let's just do when n is 0, I'm going to get a 1. So I'm going to get a 1 when n is 0, because this e to the x, whatever e to the x is, I'm going to raise it to the 0th power. That'll give me a 1 here. When n is 1, I'm going to get a minus, what am I going to get? Minus e to the x squared. So minus e to the x squared over 2n factorial. And now I'm realizing something I could have done on the last one here. Instead of writing that as e to the x squared, well, let's just leave it there. E to the x squared here, plus, not over 2n factorial, over 2 factorial. 2 factorial is 2. Plus, I'm going to get an e to the x quantity. When n is 2, I'm going to get 2n is 4. 4 factorial. Minus e to the x to the 6th over 6 factorial. And then there's some other stuff here. So what I'm going to get now is 1 minus e to the x squared. That's e to the 2x over 2. Plus e to the 4x is e to the 4x over 4 factorial is 24. E to the x to the 6th is e to the 6x. 6 factorial is 720. Plus blah, blah, blah. Okay, so what I'm going to get then is I'm going to get 1 minus a half times series for e to the 2x. So it's 1 plus, so maybe right up here, summation n equals 0 to infinity. Let's write a series for e to the x. And is x to the n over n factorial. So e to the 2x should be 2x to the n over n factorial. So this is 2x, just to the first, over 1 factorial is 1. So that's just 2x. Plus, let's see, we're going to get 2x squared over 2 factorial is 2. Plus 2x cubed over 3 factorial is 6. Let's do one more. Plus 2x to the 4th over 4 factorial is 24. Here, so that's 1 minus the e to the 2x over 2. And then let's do the e to the 4x over 24. Here, so we'll get plus 1 24th. And then the e to the 4x is going to be 1 plus 4x plus 4x squared over 2 plus 4x cubed over 6 plus 4x to the 4th over 24 plus some stuff here. And then we get plus some more of these terms here. So what we're going to end up with here is, now let's just think about what's our constant term. Well, you're going to get 1, our constant term is 1 minus a half, and then it's going to be plus 1/24th. But if you think about this, you're going to get a constant term for every single one of these here. So this is going to be a problem. So right away, I'm noticing this is actually going to be a problem as I work this out here. So cosine e to the x, 1 minus a half plus 1/24th here. That's a bit of a mess here. So 1 minus a half plus 1/24th. The next one, e to the 6x, is going to give me a minus 1 over 6 factorial, and then I'll get a plus 1 over 8 factorial, minus 1 over 10 factorial, plus 1 over 12 factorial, blah, blah, blah. Here. So that's just the constant term. So what I'm going to get is a sum, if you look at this constant term. This is an n equals 0 to infinity. What I really have is it's alternating, and then I have a 1, but I'm dividing by then, let's see, it's 2n factorial. So it's 2 factorial, 4 factorial, 6 factorial, sorry, 2 factorial, 4 factorial, 6 factorial, 8 factorial, 10 factorial, 12 factorial. This, if you think about it, this series, this is just cosine of 1. So our constant term is cosine of 1 here, which we should expect because when you plug in 0, you get cosine of 1. So all this constant term business is cosine of 1 here. So we're going to get cosine of 1. Let's look at our coefficient of x. So this is really constant term. So our answer, let's maybe put an answer, we'll put it way up here. So cosine e to the x is approximately, constant term is cosine 1. And now I want an x term. This is going to be kind of annoying here, because what I'm going to get is each of these e to the 2x, e to the 4x, e to the 6x, they all have an x term. So what I'm going to get, if you think about it, it's negative 1/2 times 2x. So I'm going to get a negative 1/2 times 2x. So it's x times. And then I'm going to get a 1/24 times 4 plus a 1/24 times 4. The next one is going to be a 6 over, really a 6 factorial. Except it's going to be a minus from an e to the 6x there. Next one will be 8 over 8 factorial, and then minus 10 over 10 factorial. So what you're going to get here is x times the sum, n equals, let's see, this is a really 1 to infinity. Looks like I get 2n over 2n factorial. And this is getting to be a mess here. So I can do this, and the problem is now, what is that number there? So is it something we're aware of? Answer is probably it's something we're aware of, but it's sort of tricky here. I guess maybe it's not that bad. 2n over 2n factorial. Let's see if we can work this out. Maybe it is bad. That'll give me a 1 over 2n minus 1 factorial. Let's see. So if you do that, if you add up 1 over x to the 2n minus 1 factorial, so that looks like, let's see, it's kind of like a sign here. So we've got odd factorials. Problem is it doesn't have that negative 1 to the n. So not real sure what to do with that as we go along. I feel like maybe this is something I should be able to recognize right now, but I'm going to say I don't know this. So what I'm going to do is I'm recognizing this is getting tricky. So I'm going to employ a totally different approach. So I have cosine e to the x. I just need the first 4 non-zero terms of the Taylor series. So my using the series didn't work. Now what I'm going to do is break down, whoops, write that more a little bit nicely. So I'm going to say f of x is cosine e to the x. I'm just going to take derivatives here. And so essentially, what I need to do is evaluate the 0th derivative, really the function at 0, and then the first derivative, and then the second and the third. So this is cosine e to the 0. That's cosine of 1. First derivative of cosine, is negative sine e to the x times the derivative of the inside is e to the x. So then f prime of 0 is negative sine e to the 0 is 1. E to the 0 is also 1. So I get a minus sine 1 for f prime of 0. So apparently this series up here was a negative of sine of 1 here. Oh, it would have worked out. I didn't have my negative 1 to the n up here. The reason why is I just forgot about it. So this should have had a negative 1 to the n up here, and then I get a negative 1, is it to the n? Yep, to the n here, and then I could have picked that out as essentially a negative of sine of 1 here. I think you'd have to shift things to make that work out and so on here. Actually, I'm a little, yeah, it should work out. Hopefully it works out. Okay, and then I'm going to do f double prime of x. I'm just looking for 4 answers that aren't 0 here. So I have to take a derivative of negative sine e to the x times e to the x. I'm going to have to do product rule. So I take the first, negative sine e to the x, times the derivative of the second, which is e to the x, plus the second times the derivative of the first. Derivative of negative sine x, negative sine is negative cosine, again, e to the x, and then times another e to the x. And so f double prime at 0, let's see, I'm going to get a negative sine 1 plus, it's going to be actually a minus cosine 1. And now I'm going to rewrite this f double prime of x because I'm going to have to differentiate again. Just want it to look nicer. So this is minus e to the x sine of e to the x. And I have e to the x times e to the x, a minus. So I'm going to get e to the 2x times cosine x. And then I can find the third derivative. So what I'm going to get here is product rule on the first term. That's first times derivative of the second is cosine e to the x times derivative of the inside is an e to the x minus the second sine e to the x times the derivative of the first That's an e to the x. So the minus is from a minus out there. And then the second one is going to look very similar. I'm going to get a minus e to the 2x times the derivative, oh sorry, not cosine x here. That should have been a cosine e to the x. So minus e to the 2x times the derivative of cosine e to the negative x. That's a negative sine e to the x times the derivative of the inside is e to the x. And then we do a product rule. We get plus, nope, it's a minus from the beginning, cosine e to the x times the derivative of e to the 2x, which is 2e to the 2x. Okay, so you get this mess here, and you could go and try and evaluate this at, or sort of simplify this down, but I'm just going to try and evaluate it at 0. I don't have to take any more derivatives unless this works out to be 0. So I'm going to get a negative, e to the 0 is 1, so I'm going to get a negative cosine 1 minus sine 1, e to the 2x, also 1 if x is 0. So I get a minus, a negative, that's a plus sine 1, and then I get a minus cosine 1. So the sine 1's cancel. If I did this right, I get a negative 2 cosine 1. So this is a mess here. But what I get is that cosine e to the x, as a series, it's going to be cosine of 1. My x term is going to be a sine 1 times x over 1 factorial, plus my x squared term is going to be really negative sine 1 minus cosine 1 times x squared over 2 factorial, and my x cubed term is going to be a minus 2 cos 1 times x cubed over 3 factorial, which is 6. So this should be my ugly answer here. All right. Ugly problem. Let's do another one. Hopefully this one works out better. I've got an extra right parenthesis here. So we're going to do tan inverse of sine of x. Here. So I'm going to do an inverse tan, or an arctan, of sine x. Now, what I'm going to need here is a series for inverse tan of x. And this hopefully works out better here. So we've got inverse tan of x here. This is a series. It's a sum. N equals, let's see, we could do a 0 to infinity. Should be a negative 1 to the n, x to the 2n plus 1, and it's just divided by 2n plus 1. So what that is if you, let's see, plug in n equals 0, you're going to get a x, and then minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus blah, blah, blah. So there's your inverse tangent x here. And sine x, remind you, turns out to be x minus x cubed over 3 factorial, which is 6, plus x to the 5th over 5 factorial, which is 120, minus x to the 7th over 7 factorial. I'm not going to worry about what that is here. So essentially, you have to put this sine x series in for each of the x's in the arctangent x. Now, before I ran into trouble, but that's because we had a constant term here. Here we don't. And so what's going to happen is your inverse tangent of sine x here, I'm going to get x. So that's x minus x cubed over 6 plus x to the 5th over 120. And then, well, I'll write the x to the 7th over 7 factorial. I'm hoping that doesn't come into play. Minus this, whoops, I should do a plus dot 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 to remind myself this goes on still. Minus x cubed over 3. Well, that's sine x cubed. So x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7 over whatever 7 factorial is cubed over 3. And I'm hoping I don't have to do the to the 5th here. Plus some other stuff. We can add that in later on, but if I go to the 5th, I'm going to end up with my lowest degree term being x to the 5th. So I'm hoping I can get away with an x term, or an x squared, an x cubed, and an x to the 4th. So let's see what happens. So to get an x here, so I'm going to get an x, I have to do an x. Oh, I'm going to need more here. So let's, sorry, I'm just looking at it. I'm going to need more. Let's do a plus This is x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7 over 7 factorial plus some stuff to the 5th just over 5. And let's do the next one as well. Minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 7 factorial plus some stuff to the 7th over 7. So it gets to be a bit ugly here. And so what I'm going to get is, how do I get an x? Well, the only way I can do that is with an x here. So I'm going to get an x. And now an x squared, well, what you'll notice here is all of the terms inside my exponents are odd. I'm going to have to take an odd number of them, either 1 or 3 or 5 or 7, so I can only get odd powers of x. So I'm going to get an x, so the next thing I can possibly get is an x cubed. Well, what I've got here is plus negative x cubed over 6 from the first term. I can get an x cubed from the second one by taking x times x times x. So it's this thing in parentheses times itself 3 times. Take a term, 3 terms, 1 from each of those, make them all x. So I'll get a minus x cubed if they're all x, but then it says to divide by 3. So I get an x, I get an x cubed. What about an x to the 5th? Well, I can get an x to the 5th over 120. And now, when I multiply 3 of these together to get an x to the 5th, I could take an x cubed over 6, negative x cubed over 6, once, and 2 x's. Now, there'll be 3 ways to do that. You can take the x cubed over 6 with the first factor, x cubed over 6 as the second factor, or the x cubed over 6 as the third factor. So what I'm going to get is a, oh, I made a mistake here. So it was x cubed, no, it's not. It's minus x cubed over 3, previous one. So I'm going to get a minus. I'm taking 1 x cubed over 6, so it's really going to be a plus in the end. I'm going to get a 1/6 here, so it'll be x to the 5th over 6. But then I have to multiply it by 3 because there are 3 ways to do that. But then I divide by 3 because I sort of have a 3 from the Taylor series for inverse tangent. So those 3's cancel. And then I could get an x to the 5th over 5 by just taking x times x times x times x 5 times from this sort of to the 5th, really the sign x to the 5th. And then the next one, I can get an x to the 7th, negative x to the 7th over 7 factorial. And then to get an x to the 7th, now this starts getting complicated here. I get 3 things here. I can either do a 3, and a 1. So that would be a minus. Here I'm going to get a 3 and a 3. So it's going to be x to the, x to the 7th. A 3, and a 1. X to the 7th over 36. Or I could do a 5 and a 1 and a 1 plus x to the 7th over 120. Both of those are divided by 3 from the outside. If I'm going to get an x to the 7th from the to the 5th term, I can do a 3. See, I could get a 1, 3, and 4 x's. So that's going to be a minus 1/6. Oh, here I didn't get my multiplier. So I said this was x to the 7th over 36. That was take 2x cubes, 1x. There's going to be 3 ways to do that. Pick which one of the 3 factors is the x. Here is a 5 here, and then 2 1s. There's going to be 3 ways to do that as well. Here. And then the x to the 7th. Here, let's see. This one, I can get a 7th by doing 2 3s and a 1. So there's going to be 3 ways to do that. Times the 1/6. X to the 7th divided by 5. And then this last one, there's going to be a 1 way to do that. X to the 7th over 7. Okay, so there's what we get for first 4 terms. I'm not going to bother simplifying that, but you get some numbers there. Bit of a mess, but you can kind of see what would go on here as we do this. And I think that's it.